My name is Tom de Saules, and I'm a building services engineer by profession. My colleagues like to call me a building physicist, but I think that's probably not strictly true. And I'm going to run through what are arguably the top 10 tips for energy efficient design and comfort. And I'm mainly talking about masonry homes, and a lot of what I'm going to cover applies not just to homes but other buildings as well. And I'm talking about year-round energy efficiency, so I'm not just concentrating on the heating season. I'm talking about the summer as well, and I think that's particularly important given the warmer summers that we are experiencing. And just to underline that, I came across an interesting statistic a few weeks ago from the Netherlands Environmental Assessment Agency, and they're predicting that by 2060 the amount of cooling that's used on a global basis is going to exceed the amount used for heating. So it's a tipping point, which is very interesting. Anyway, on to my first point, which is building orientation. It's not something designers and developers and architects are always able to control and influence, but if you can, it makes really good sense to orientate dwellings on a north-south axis. And there's a lot of good reasons for doing that, which will become more apparent as I carry on. But essentially, it gives you a really good standard of daylighting. It avoids glare. It provides passive solar gains during the heating season. And it makes shading very straightforward. And you'll see why shortly. So following directly on from that, if we have got a north-south orientation, what we want to try and do is to have a 2-to-1 ratio in terms of glazed area. So we want roughly twice the amount of glazing on the south elevation than on the north. And the reason for that is that on the north elevation, windows actually have a net heat loss over the course of the year. So really you want windows that are just big enough to meet your daylighting requirements, but nothing more than that. But on the south elevation, we really want to try and optimise the glazing to get as much solar gain as we can during the heating season without inadvertently leading to overheating problems in the summer. So on this example of an ordinary detached house, probably want about 13 metres squared on the south elevation and about half that on the north. Now the other point just to make before I move on is that this is the essence of passive solar design. It's about window design and orientation, and this dwelling has been optimised to take advantage of that, and it looks conventional. So passive solar design doesn't mean you need an unorthodox or unconventional appearance to your building. You'll see that all of these points are linked, they all work together. So at number 8, we've got solar shading. Now on our south elevation, shading is very straightforward because we can do it with an overhang, could be a balcony, brise soleil, an awning, or maybe just a deep overhang on the roof for the first floor. And that will keep out the high angle summer sun but won't block the winter sun. So shading's very easy. Now on the east-west elevations, it's a little more tricky. We can't use an overhang, it's not going to work, it's not going to keep out the low angle sun in the east in the morning and in the west in the evening, so we're going to have to use shutters or blinds. And actually external shutters is one of the best options you can use, and it's not popular in the UK. You see them used widely in mainland Europe, but not in the UK. I think that's probably set to change in the next few years because we're going to get much tougher legislation on overheating and on ventilation as well in the summer. And external shutters are brilliant because not only do they keep the sun out, they provide a means of secure ventilation as well. And depending on the design, they can also reduce heat loss during the heating season if you keep them shut at night. And it's always a good idea to have your shading on the outside of the building as well if you can. That's where it's most effective. So, as I say, probably see more external shutters in the UK in the future. And just to make the point about how effective overhangs are at keeping out the summer sun, this is a quick simulation in Google SketchUp, which is a very useful tool because it allows you to look at sun paths and shading, and you can specify where in the UK your building is, the orientation, the time of day, the time of year, and you can see what actually happens. So this is a south-facing room, south-facing windows. We've got a brise soleil overhang, It's 7 o'clock in the morning, and as we go through the day, you'll see it's doing a pretty good job of keeping out that high angle summer sun and helping to prevent overheating problems. And in a minute I'll show you this model again, but on a day in the heating season. Okay, number 7 is ventilation, or summertime ventilation. Now, when we talk about ventilation at the moment, it's nearly always in the context of the heating season and trying to have a minimal amount of ventilation. You've got just enough for occupant needs and no more, because you don't want excess heat loss. That's fine, but we don't necessarily give enough attention to summertime ventilation, where we need much larger volumes of air to keep the building cool. And these are just a couple of really effective techniques that you may be familiar with. So we've got cross ventilation, where you've got openings on opposite sides of the building, and the wind can blow directly from one side to the other, and you just need to make sure that air path is not obstructed, and you can get very high air change rates with this. It's probably the best option to go for summertime ventilation. Stack ventilation on the right, this works where when the wind isn't blowing, or maybe in locations where you have low wind speeds. And this is relying on the natural buoyancy of warm air to get air through the building. So the way it works is you've got low-level openings. They allow cool air in, particularly at night, so you keep those open at night. That cool air picks up heat inside the building, so it's drawing heat out of the fabric, and as it does so, the temperature of the air increases, it becomes more buoyant, and it rises up to the top of the building. So you need to design the building so that it can go from one floor to another. And then it leaves through these high-level windows or some other form of opening. So it's, as I say, really good in urban locations and where you've got low wind speeds. And of course you can use the two together as well. So that's all well and good, but one of the issues we're going to have to contend with going forwards is security. And there's very recently been a change to the SAP overheating assessment, which is the compliance tool for the building regs. And in the past, you were able, when you're doing your SAP assessment for overheating, just to assume that windows could be left open and you could get large volumes of air. Can't do that anymore. You have to look at the local environment, and you have to do an assessment to see if there's a potential security issue and also a noise issue as well. And if there is, and you don't do anything about it in terms of ventilation, you have to assume that you've only got trickle vents for your summertime ventilation, which of course not going to work. You'll fail the test straight away. So we're going to have to give a lot more thought to how we provide summertime ventilation. And this slide just shows a few options for addressing security. So we've got here we've got ventilation opening, which has a little door on the inside and a fixed louver grille, so that provides your security. Quite often they have an insect screen over them as well, keep the bugs out. And the occupants could just open and close that door to regulate the airflow. And importantly, keep it shut during the heating season when we don't need that extra airflow and we want to reduce heat loss. And the door itself's got a bit of insulation in it. Now, an alternative to that is sliding screens, which go across the face of ordinary windows. Those are becoming very popular at the moment. And on the right, that's an example of some dwellings that use the stack ventilation system, which I mentioned just now. So you can't see it in this picture, but there'll be fixed low-level openings with some sort of security grille over there. As I said, air comes in at low level, picks up heat, rises up to the top of the building, and then leaves through these ventilation chimneys that they've got on the roof. And these were actually custom made on this project out of plywood with a lime render finish. I should have said it's called the Triangle, and it's in Swindon. Now, the brilliant thing about that design is that the stack ventilation system, it addresses a security issue with your fixed low-level opening with some sort of grille over it or steel mesh. It will address the noise issue as well if you can locate that opening away from busy roads, maybe around the back of the building, and ideally on a north elevation as well, so it'll be drawing in cooler air. And it'll also improve air quality as well if you can keep it away from busy roads, and that is something you do have to consider if you're building dwellings in London. Okay, number 6, use of thermal mass. Now, thermal mass is a property of medium and heavyweight materials, so you'll find it in masonry and concrete and stone. And if you're not familiar with it, basically it just describes the ability of these materials to absorb heat and hold on to it and then release it later in the day. So it's a very effective way of helping to prevent overheating when you've got hot conditions, because it will soak up unwanted heat inside the building and help stabilize the internal temperature. But you do have to get rid of that accumulated heat, and you do it at night using the cool nighttime air to draw heat back out of the fabric, cool it down, so the next day it's ready once again to provide a lovely radiant cooling effect. So what are the key sources of thermal mass in a dwelling? Well, you can see them in this cutaway. You can have a concrete upper floor as an alternative to a timber upper floor, and I've put on this slide the K values for each of these building elements, and just briefly, that's the measure of thermal mass used in SAP and SBEM, the compliance tools for Part L. So with a concrete upper floor, you've got a K value of between 40 and about 160, depends on the type of floor and type of finish. Just to put that into context, a timber upper floor will have a K value of about 18 kilojoules per metre squared. Lots of thermal mass in blockwork partitions, between about 39 and 111. And similarly in cavity walls, loads of thermal mass in the inner leaf of blockwork, and get up to 190 kilojoules from your blockwork. Timber frame, external wall, you've only got the thermal mass of the inner leaf of plasterboard, so you have about 9 kilojoules, so it's quite a bit less. Now, one thing just to mention is that people think that if you dry line the walls, that will kill the thermal mass, and it certainly reduces it, but not to the extent that you might think. And if you actually compare the K value of a dry lined masonry wall with a wet plaster one, it's only about 20% less, so it's not huge. And lots of thermal mass in concrete ground floors as well, particularly if you tile them, which not only adds to the thermal mass, but it will conduct heat to and from the screed or the slab underneath very freely, which is a good property. So back to that simulation. So same room, but now it's a day in February, so we're in the heating season. It's 8 o'clock in the morning, and the low angle sun is already shining underneath the overhang and onto the side wall there. So if you've got a bit of thermal mass in that wall, it's going to be absorbing the free passive solar gains and holding on to those. And then we'll just go through the day. And you can see the sun tracks round onto the floor again. If it's a heavyweight floor, it's holding on to some of those solar gains. And then by about 4 o'clock, the sun's gone down and it's all over. And then what happens is the air temperature drops and some of the heat stored in the fabric is re-radiated back into the room. And that can actually reduce the load on your heating system by around 11%. Doesn't sound massive, but over the lifetime of the building, that will add up. And you have to also remember that it's not really adding anything to the cost of the design. It doesn't require any user interaction. It doesn't require any maintenance. So it's going to be doing this for the life of the building. And if it's a masonry building, I would argue it's going to be around for a very long time. Just finally on thermal mass, we often get asked where should it be located, and it's a very easy question to answer because essentially it has to be exposed to the inside of the building. So if you've got a cavity wall, which you can see at the top, that's fine. You've got that inner leaf of blockwork, so that can absorb and release heat gains. Solid masonry construction in the middle, again, that's fine because it's good practice to put the insulation on the outside of the building, so you've got all the mass of those nice thick blocks. What you don't want to do is to insulate internally if you can avoid that, because it isolates the thermal mass. So from a thermal mass perspective, something like insulated plasterboard is not great. Same rule for ground floors. As I said, tiles are brilliant. They will conduct heat to and from the screed and the slab below freely, and also add a little bit of thermal mass as well. So number 5, efficient heating, and I'm just going to carry on with the theme of ground floors for a moment. You can see here a cutaway of a heavyweight ground floor with a wet underfloor heating system. And in this example, the insulation is underneath the concrete slab. Now that's not particularly conventional, but there's absolutely nothing to stop you doing that. And if you really want to max out on the thermal mass, that's the place to put it, because you've got all the mass of the slab, the screed, and the tiles. The only downside is you get a very slow response time in terms of heating controls. But that doesn't really matter in reality, because with this arrangement you really want the heating on all the time at very low level, just in the background. That's a very efficient form of heating. And the reason why it's particularly efficient is because if it's linked to a condensing boiler, so that's supplying your underfloor heating system, it will be able to operate in condensing mode for very long periods of time, which is when it's most efficient. The reason being, without getting too technical, the flow and return temperature to the floor can be about 10 degrees lower than would otherwise be the case in a lightweight floor. And condensing boilers love that, so that 10 degree reduction will improve the performance by about 5%. Again, doesn't sound huge, but over the life of the system that will add up. But perhaps more importantly, if we're using a heat pump instead of a condensing boiler, which we will be in the future, we're going to be moving over to heat pumps, that 10 degree reduction in flow and return temperature will give you about a 20% uplift in performance of your heat pump. They are very sensitive to flow and return temperature. So I would argue this is a very good arrangement if you want an efficient heating system. Oh, actually, just one other point, just before I move on. The other thing with heat pumps is they're electrically driven. We're all getting smart meters now. We're going to get real-time energy pricing in homes, and soon we'll be able to switch on the heat pump when electricity is cheap, store the heat in the floor, take advantage of that later, so we'll save on our heating bills, and we'll also be doing the whole of the UK a good service because we'll be making greater use of renewable energy when it's abundant, because we can do that, because we can use it when we don't actually need it and store it in the floor. Okay, number 4, airtight construction. Goes without saying, we don't want too many gaps and cracks in our homes and buildings. The thing I want to say about this is that in 2006 we had to start pressure testing new homes. It came into the building regs then, so it was mandatory. And what we found initially was that timber frame homes were performing slightly better than masonry homes. And the reason for that was that they have a vapour barrier, which also, as it turned out, acted quite well as an air barrier. However, since then we've learnt lessons on how to design masonry homes and build them as well to ensure they're airtight, and today they're as airtight as any other form of construction, so it's not an issue anymore. And in fact, if you look at NHBC pressure testing statistics, it's masonry homes that are the most airtight, which is quite interesting. Now, one other thing to mention on airtightness is it's all very well passing the test when the building's new, but you do need to maintain airtightness over the life of the building. And the NHBC Foundation did some research a few years ago to see how well new homes performed when they were sort of 4 or 5 years old. So they went back and retested them, compared the results with the original pressure testing results. It was a fairly small sample, but what they found was it was the masonry homes that were maintaining a high standard of airtightness. It wasn't degrading as rapidly as the other methods of construction. So that was good news. And I mentioned wet plaster finishes earlier, great for thermal mass, also brilliant as an air barrier, very effective, very robust, and the brilliant thing about it as well is that unlike other air barriers, you can actually see it, so if it becomes damaged, you can repair it. So it'll maintain its integrity over the life of the building. Okay, number 3, minimising thermal bridging. Of course, the thermal bridge is anything that crosses or spans your layer of insulation and is a source of heat loss. And if you look at the SAP assessment tool, there's a little box you can tick for the default thermal bridging value, which is a very tempting thing to do because then you can just move on, it saves time. But you'll pay a very high price for that because SAP will assume up to 35% of the heat loss from your dwelling comes from thermal bridging. So much better to take a little bit of time and trouble to specify the individual thermal bridges, and you'll get a much better result. And the masonry sector has produced a comprehensive set of high-performance construction details which are free to download and use. We've got details for aggregate blocks, get those from the CBA website. Details for aircrete blocks, get those from the Constructive Details website. Or alternatively, you can just go to the LABC website and you'll find all of them there, not only for cavity wall construction, but also for solid masonry. So I do recommend, if you're building in masonry, you use those. It's a very cost-effective way of maximising thermal efficiency. And if you do, you'll go from about 35% with that default thermal bridging value down to about 14. So it's a bit of a no-brainer, really. And we've also got loads of relatively new high-performance ancillary products for masonry construction that reduce thermal bridging. So we've got insulated cavity closers made from plastic with a polystyrene core. You just cut them to size and they slot together, very easy to use. And they'll take the weight of a triple glazed window unit, which you can sit on the cavity closer, which is, from a thermal efficiency point of view, the best place to put it. We've got high performance lintels from companies like Keystone, give you very low SI values. We've got high performance wall ties now, and you can see both of these examples on the Ancon stand, which is just over there behind you. And they produce basalt fibre ties, which is the black one at the bottom. They're made from the basalt mineral mixed with a epoxy resin, and they essentially don't conduct any heat at all. You don't even have to enter their details in your U-value calculation. They're that good. You pay a little bit of a premium for those, but you can still use wire ties like the one shown there. And the only thing I'd say about those is we've got really good ones now for larger cavities. So 150mm cavities, you can now get a Type 4 wall tie, and the significance of that is that a Type 4 tie is very, very thin, conducts virtually no heat. Couldn't get those a few years ago. You'd had to have used a really thick, chunky tie, would have lost you loads of heat. Not the case anymore. Okay, number 2, insulation. The more the better, of course. What I want to say about insulation in respect of masonry construction is that it was thought a few years ago you might need walls that like 1/2 metre thick to get the sort of U values that were required for zero carbon homes. Hasn't turned out to be the case at all. We've had some really high performance insulation products come onto the market. Will give you a U value of about 0.18, which is excellent, good enough for Partel, in a standard 100mm cavity. So no need for really wide cavities if you don't want them. Do pay a little bit more for these, but you can get the same level of performance with more conventional options, albeit in a wider cavity of 150mm. So that could be partial fill or full fill mineral wall insulation, which is the cheapest option of all. And then just before I move on, I just want to mention beam and polystyrene block ground floors, which are very popular these days. This is where you use polystyrene blocks to infill between your concrete beams instead of concrete blocks. And they obviously provide the insulation, but they also, in doing that, reduce the overall floor depth, so you don't have to remove so much soil from site. And there's products available now that can give you fantastically low U values of 0.09, way better than you need for Partel. So I just wanted to make you aware of that. At number 1, perhaps controversially, but I think the most important thing is to make sure that the home is resilient and durable, because there's no point in going to the trouble of maximising the fabric energy efficiency if the home itself isn't fundamentally durable. And when I say resilient, I mean resilient to the effects of climate change, so overheating, which I spoke about, effects of flooding, you need flood resilient materials. Durable, masonry and concrete is extremely durable. It also protects the thermal performance in as much as the insulation in the cavity is well protected. I mentioned wet plaster as your air barrier, very robust, and as I said, you can fix it easily. So I think this should be number 1. Make sure that buildings are durable, and people don't really talk about that much at the moment. So I wanted to bring that to your attention. And I think I've still got a few minutes, hopefully. So I just wanted to go back to one point that I raised earlier very quickly and just go into a little bit more detail, which is summertime ventilation and this new requirement to think about acoustics and security issues. I mentioned security. I was going to talk a little bit about acoustics, and I've cheekily borrowed a few slides from a CIBSE webinar which I saw last year, which was a really useful webinar, so I wanted to share them with you. And it was by a chap called Jack Harvey Clark and Anthony Chilton, and basically they were just talking about a new assessment methodology for considering acoustic performance in the overheating condition. And what I mean by that is that they've identified there's plenty of guidance on dealing with acoustics from mechanical services. CIBSE published guidance on that. There's a British standard on dealing with acoustics through facades, but there's nothing on dealing with acoustics where you've got windows that are open, so in the overheating condition. So they've come up with a very simple 2-step test that you can apply, and I'll just take you through it. So 2-level assessment procedure. Level 1, what you have to do is go to site, do some sound level, do a sound level assessment both during the day and at night, come up with your average values, and then all you do is you knock off from those values 12 decibels, and that represents the difference between the outside noise level and the inside when you've got a window that's wide open. So it's sort of worst case scenario. And if in that worst case scenario you still come in under 50 dB during the day, 43 at night, then you've passed the level 1 assessment and you don't need to do any more. You can just ventilate your building with windows that are open, assuming, of course, you haven't got a security issue. If you fail it, then you've got to go into a bit more, effort with your design. And on this table, you can see that high level again at the bottom, the 43 and the 50 dB, and then you've got the other levels for medium, low, and negligible. Now, we've already established that the open window is not going to work, so we've got to think about using some other approach. And here are some options. And at the top, you can see your standard open window and the 12 dB reduction. And then we've got things like balconies, acoustic balconies will give you a greater sound reduction. Attenuated windows and attenuated vents is the best of all. So you might want to apply one of those. And this is what they look like. So attenuated windows and vents, basically they provide an indirect path for the air and for the sound as well. And here's a very quick case study just to finish off. So this is St John's Hill in Clapham, residential development. They did this assessment on the development, and what they found was with the level 1 assessment they failed it at night. So with an open window wasn't enough. We've still got 48 dBA inside the building, which is higher than the 43 dBA limit. So open all windows no good. So what they did was they decided on attenuating vents in the end, and you can see a couple of photos there of the final solution. And with those, with the level 2 assessment, we passed that now, because instead of the 12 dBA reduction with the open windows, we've got a 24 to 27 dBA reduction. So we're now in the medium risk zone. So that's okay, as long as we're not in the high risk zone. So very simple methodology. And if you want to know more about that, there's some relevant websites and the email addresses of the guys who did the webinar. That won't be up for long, but if you want that, come and see me afterwards. I can give you the contact details. And you can download the full report from CIBSE. So finally, if you want to know more about thermal mass, we've got a publication called Thermal Mass Explained that will take you through the basics. They are on our stand just over there. You can see the big concrete future sign, so help yourself to one of those. If you want to know more about Part L of the building regs in respect of masonry, then have a look at the publication in the middle. You can download that from our website. And at the back, you'll find a table that runs into several pages of lots of different forms of masonry construction. And for those, you'll find corresponding U values and a whole variety of thermal mass information, so K values, admittance values, decrement values, it's all there. So useful stuff if you're doing a summertime overheating assessment. And then finally, if you're interested in thermal mass in commercial buildings, have a look at the publication on the right. It will take you through all the various techniques of using exposed soffits, and lots of case studies in there. And if you want to know more about masonry, we've got some very simple, easy guides that will provide an introduction to cavity walls, beam and block ground floors, and concrete blocks. So it'll explain the different types of concrete block, their applications, and the different sizes. And you'll find those on the modern masonry stand, which is about 20 yards behind you. So thank you very much. I hope that was of some interest to you.